So we're going to continue with complex numbers, and before I get started, I didn't put this in the last one, but the standard form of complex numbers is the a plus bi. And the a is going to be represented as the real part, the part without the I. The bi is the imaginary part. You always want to put that real part first, and then plus or minus the imaginary part after that. So for one like this, the first one, understand this is not 3 plus I, this is just 3I. This is one term right here. So all you're doing is distributing this, okay? And just like before, these work very similar to normal variables. So all I'm doing is distributing. 3I times negative 5 becomes negative 15I plus 3I times 2I, that becomes a positive 6I squared because it's I times I. And then the only thing I have to do from here is remember that the I squared is equal to negative 1. And so when I do that, that's going to become negative 6 minus 15I. And I'm moving that to the front so it's in the standard form, and that's the real part. And I get that as my simplified form. The second one is two binomials. And if you remember the two binomials, all you're doing is distributing twice. First distribute this 4, and then distribute the 3I. A lot of you guys will remember it as FOIL. We're not supposed to say that anymore though. Okay. But distribute the 4, I get negative 4 minus 8I, then distribute the 3I, negative 3I, and this becomes negative 6I squared. And now combine my like terms, I get negative 4, this becomes minus 11I, but this also becomes that negative 6 times negative I becomes positive 6. Remember that basically all you need to do is when you get rid of this I squared, because it becomes negative 1, you multiply by negative 1, which really just changes the sign. So as long as when you get rid of that, change that sign, and you're all good. And now I can combine this negative 4 and positive 6, and that becomes positive 2, and I'm writing that real part first, minus 11I. And pay attention to what's happening with each term in each polynomial, each binomial. Again, people will do this first one just like this second one, and they're different. This is not 3 plus I, this is just 3I times negative 5 plus 2I. And other times people will, when you have two parentheses being added together, they start the multiplying process because you see two parentheses, oh, I got to multiply. Pay attention to what's happening to each binomial, each term. So like for this one, I have 2I plus this parentheses minus 3 times this parentheses. So to simplify it, I'm going to get rid of the parentheses first. The 2I is not being distributed to this one. It's 2I plus 4 minus 5I. And because that's a plus, nothing changes to that. But in this one, I have this negative 3 times this binomial, so I'm going to make that negative 6 minus 9I squared. And now I'm going to combine my like terms. I have this 2I, negative 5I. I have this 4, negative 6. So the 4 minus 6 becomes negative 2. 2I minus 5I becomes negative 3I. And this negative 9I squared is going to become positive 9 because the I squared is negative 1. And now I can combine these two, which now that becomes positive 7 minus 3I. And for this last one, when I distribute twice, I first distribute the negative 6, that becomes positive 36, plus 6I, this becomes minus 6i, and this becomes positive I squared. 36, these two will cancel out. And then this, because it's just I squared, becomes minus, and that coefficient is 1. So it becomes 35. Well, what happened here is that when I multiplied these two imaginary numbers and these two complex numbers, it came out to a real number, a number without an I. And the reason that is because these two have a special pattern. Negative 6 plus I, negative 6 minus I. When you have that pattern, this is going to happen, that they're going to multiply to be a real number. And that leads us into the next part, which is dividing. That pattern, when the A and the BI are the same, the real part and the imaginary part are the same. The only thing that you have different is this sign in the middle. And basically that means that the imaginary part are opposites of each other, but the real parts are the same. They're called complex conjugates. And what you need to know and understand is that when you multiply complex conjugates, they multiply to be a real number. It's very similar to that difference of squares where you have a plus b times a minus b becomes a squared minus b squared. And that middle term will cancel out. Well, the middle term is where the i's come from, and that last term is going to be the I squared, and that's going to become a real number. The first one is a real number, so there's no more i's anymore, and it becomes, the whole thing will become a real number. And we need to know that and understand that in order to divide. Because what you can't have in a fraction or in a division problem is a radical in the denominator. And anytime you have an I in the denominator, you got to understand that that I really is a radical. So I have to, it's called rationalizing the denominator, and I have to get rid of that radical in the denominator. So to get rid of this I, or the radical in this denominator, what I'm going to do is I'm going to multiply it by its conjugate. Well, this one's very different than the other ones. This one's just the I part. So what I'm going to do, this is really just understand this as 0 plus 3i. So its conjugate is going to be 0 minus 3i, which is really just negative 3i. So I'm going to multiply by negative 3i here, multiply by negative 3i here, and you multiply both top and bottom, numerator and denominator, by that conjugate, and I distribute, and that becomes negative 27i minus 30i squared over, and this becomes negative 9i squared. Negative 30i squared just becomes positive 30, and minus 27i over, and this becomes positive 9. And now what I can do actually is simplify. They all can reduce by 3, so I get 10 minus 9i all over 3. If you wanted to simplify this more, when you're simplifying, what you have to do is, I'm okay to simplify just looking at all three parts and what goes into every part, because you have to understand that this is 30 over 9 minus 27i over 9. This would be another way to write this same fraction. So in order to simplify, all three parts have to be divisible by the same common factor, or you could split them and simplify them individually. The 30 minus 9 becomes 10 over 3, and the 27 over 9 becomes minus 3i. And you could do it that as well. Either one of these I'm okay with. Okay, so for this one, I can't have this I in the denominator. So what I have to do is make that a real number, and what I'm going to do that is multiply by its conjugate. And the conjugate of 1 minus 4i is going to be 1 plus 4i. And understand these are two binomials, so I'm going to have to distribute twice. And so the top, I'm going to go a little quicker on this one to save time. And I'm left with this the two i's in the middle combine to be 11i, and this becomes minus 12. The two i's in the middle and the denominator, they cancel out, which they should. That's if they're not canceling out, it's not the conjugate. And this is left with 1 plus 16, and then to simplify those, I get negative 10 plus 11i over 17. And that can't simplify. Nothing goes into 10, 17, and 11. 17 and 11 are both prime numbers, and so that is it. And for this last one, this messes some people up. A couple things to remember. You're multiplying by the denominator's conjugate, and you multiply the same thing to the numerator and the denominator. So the denominator's conjugate here, and what messes people up is this negative sign here. That stays the same. That is still going to be a negative 3. That doesn't change. The only sign that changes is the one between the two real part and the imaginary part. So the conjugate of negative 3 plus 4i is going to be negative 3 minus 4i. And so when I distribute, I get negative 15i minus 20i squared. Remember that this is just a monomial. It's a one term, 5i, and all I'm doing is distributing that 1. I'm not doing the FOIL or distributing twice because it's not a binomial. I am doing that here. The i's will cancel out. The numerator, the I squared, makes this a positive 20 minus 15i. The denominator becomes 9 plus 16. So I get 20 minus 15i all over 25. Can I reduce? Yes, they all reduce by 5. So I'm left with 4 minus 3i over 5. Okay, so something else we need to get down is the i's being raised to exponents. And we know that I to the first is just I. We also know that I squared becomes negative 1. And based off of those two, we can figure out all the other ones. I to the third, well, I to the third is going to be I squared times I. So what this means is that I have negative 1 times I, which is negative I. And I to the fourth, you can look at this two different ways. I to the fourth is I squared times I squared, which is negative 1 times negative 1, which becomes positive 1. And after that, once you get I to the fifth, you start over back here. So because I to the fifth is just I to the fourth times I, well, that's going to be 1 times I, which is I. And then I to the sixth is I to the fourth times I squared, so that's going to be negative 1. What you need to know is this pattern here, because all the exponents of I repeat as a pattern of 4. I is equal to I squared is equal to negative 1, I to the third is equal to negative I, and I to the fourth is equal to positive 1. And all the other ones just start repeating after that. The way I remember this pattern is a goofy saying. You know you like my goofy sayings. And it's a question. What do you say when you win the lottery? I won, woohoo! But I won, but I lost a little bit in the middle because I had to use all that money to buy 4 years worth of lottery tickets. Hopefully it's only 4. So what you need to look at basically is what you do is you take this exponent, divide it by 4, and it doesn't matter how many times 4 goes into that. What matters is the remainder. 4 only goes into it once, but the remainder is equal to 3, and this is what's important. So because the remainder is 3, it's going to be similar to the I to the third, and that is going to be equivalent to I to the third. So that means that I to the seventh is equal to negative I. And so I to the 12th, because 4 goes into 12 evenly, what it means is it's similar to I to the fourth, because 4 goes into 4 evenly. So anytime 4 goes into it evenly, it's equal to 1. So you try these 2. Pause it, take a second, try them, and I'll give you the answers. And so for number 10, it becomes I because 4 goes into 36. And so that means this is 1 remaining. So it's the same as I to the first. And this is going to be the same as I squared, which is -1. Again, it doesn't matter how many times 4 goes into 58. What matters is that it has a remainder of 2. 4 goes into 56 evenly, so it has a remainder of 2, which means it's the same as I squared. Okay, this last part we're going to get back to solving quadratics, and these are going to be solving quadratics by square roots. And I can only solve by square roots if I have this missing term of x, of the x term in the middle, and I only have the x squared term and the constant. So what you want to do is to solve by square roots. I want to get the x squared by itself. And so in this case, I want to add the 45 to both sides. And I'm left with x squared equals 45. And then I can get the x to just become x by doing the inverse operation. Well, the inverse operation of squaring something is taking the square root. And so when I take the square root of both sides, I'm left with x equals, and one important thing to remember here is that when I take the square root of both sides, I always need to have this plus or minus. And so when this becomes plus or minus, it becomes 2 answers because, and simplify the radical, it's not a perfect square, so you do need to simplify it. I'll do my perfect squares, and I have square root of 9 times the square root of 5, which becomes 3 square root of 5. And so x is equal to plus or minus 3 square root of 5. And that's it. These are done. These go very quick, but you have to know when you can use them, when you can't. So for this next one, I get subtract the 64 to get the x squared by itself. And I get x squared is equal to negative 64. And then I take the square root. Even though I'm taking a square root, I'm taking a square root of a negative, I still need this plus or minus because I took the square root of both sides. And so what this negative does, because it's inside the radical, remember what happens is that the I comes on the outside. And the square root of 64 is 8, so this just becomes plus or minus 8i. And I'm done. I'm done. Yeah, I'm done. And so here, I do have an x, okay? But when I get everything to one side, what happens is that this x will cancel out. And now I don't have an x term anymore. Now I can solve by square roots. So now I want to bring this constant to the right side. And before I take the square root, I always
What do you call a gorilla with a green thumb? Harry Potter! Get it? Because it's Harry. He's Potter. He's got a green thumb. Gardener. He puts things in pots. Potter. Harry Potter.